You are online.
Thank you, Misha. So I would like to thank the organizers and Misha especially for giving me this opportunity to talk here in this beautiful audience, and so many people whom I know and have collaborated before. So this workshop is about impurities. So I felt obliged that I have to make connection of my work to the impurities, even though you will see it has nothing to do with impurities, but there is a one underlying thing, and I would like to come to this thing in the very beginning, so you can keep this in mind. So just before I begin, this is work which we were doing with my PhD student James Pallister from the University of Birmingham and Sasha Abanov from Stony Brook University, and to whom I am indebted for many help and discussions. So that goes. So the story about impurities. Okay, sorry. Right. Okay, so there was a model which we developed, me and Sasha and Alex Kamenev and his PhD student Mike Schechter, called model of dipleton, to describe a slow, heavy impurity. Well, the precise conditions are being debated right now in the quantum one-dimensional liquid. And we call this model dipleton because we considered a impurity, some atom which is not like the other atoms in the superfluid background, which repels the atoms in the background. And we did all kinds of things with that. We tried to drag it with external force. We looked at the stability of the superfluid motion, whether it gets stopped by the thermal fluctuations in the background, and so on and so forth. I'm not going to talk about this today. But what I'm going to talk about is the model itself. So it represents the following addition to the background Hamiltonian or the action. The background Hamiltonian is traditionally and successfully described by Latinger liquid, which is essentially a theory of one-dimensional phonons, sound waves propagating on a flat background made of fermions, bosons, spins, you name it. So you can see this action here. Most of you are familiar with that. In addition to that, we put a particle which has to interact with this field. In fact, we can naturally separate our system into two parts. One is the background one, which is extended system, but it's mostly taken to be a linear system. And another one is local, but a non-linear system. In many cases, to write the first part, which is the sort of action of a dipleton, is we use some phenomenological approach. So based on the knowledge of the dispersion relation. And there are some interaction terms. I'm not going to discuss how we obtain them, but essentially the dipleton is characterized by, apart from its momentum and position, so we assume some kind of semi-classical approach, it's also characterized by the number of depleted particles and the phase jump. And this, in a steady state, these two numbers are Boring constants. But in the dynamic situation, for example, when this impurity is dragged by external field, these fields gets their dynamics and they actually interact with the external, with the background fields, theta and phi, which represent essentially density and, well, the integral of density and the integral of velocity. Right. And essentially, this impurity description is a way to parameterize some important non-trivial configurations of my system. Essentially, It's not only, so they're nonlinear. So essentially, I'm talking about configurations of the background field, which include this kind of deep near the particle, which is not captured by Latinger liquid behavior. So here schematically, I represent these configurations. Now I will probably talk a little bit more about it. So why these configurations are important, why we can't do without them. So let's look at an example of calculations which people were doing, which essentially were using the same approach apart from the numerical people. But this approach was pioneered by Kamenev, Glazov, Pustilin, and Khodas, Imanbekov, Vadim Shayanov, Misha Zvonarев. Then there were some numerical works by Jean-Sebastian Coe and Calabrese, and then I contributed a little bit to this as well. So let's take dynamical structure factor of the impurity. So essentially, the response function, which tells me how can I excite my system as a function of external probe, which depends on momentum, horizontal axis, and external frequency omega. So I can excite excitations in my system only for a certain, essentially for a certain conditions on these two numbers, and also the sensitivity of my system depends on my position. So mostly especially for small momenta, most excitations of my system are phonons, and most of the weight, so at least Latinger liquid predicts that all you can excite are this phononic, along this phononic line, which is, you probably can see there. But if you are interested in the response of the system, and the response of the system can be strong away from this line, the Latinger liquid cannot answer this question at all. You really need to find some other non-perturbative configurations in the system to answer this question. That was the main idea behind these calculations. So one way of look at this, and one way to look what are the configurations which are really can answer the questions near the so-called spectral edge, either up or down the phononic line. Below, by the way, the lowest line, there are no excitations at all. That's a feature of one-dimensional systems. We take the following thing. We create the configurations I'm talking about is to create a dipleton at some point x1, t1, and propagate it for some times and destroy it at x2, t2. Then to calculate the corresponding optimal configurations of density and velocity, substitute it into the action, and take this as into the exponent. This will essentially give pretty much the answer. Here I write my correlation function, the function of the time and space difference, but you can already see that it has in the exponent the line of the impurity, so momentum and its dispersion, and it also encodes the power law, which will after Fourier transform will become the answer to these questions for the dynamical structure factor. So this is the configuration which dominates the response away from the Latinger liquid, and this actually was deemed to be so-called non-linear Latinger liquids. And there's an article in the review by Imanbekov, Schmidt, and Glazov. Right. So that's the story. Essentially, I'm interested in the non-perturbative configurations of, say, this approach, by the way, is purely hydrodynamical. So I'm interested in non-perturbative hydrodynamical configurations, and you will see there are can have very beautiful. I mean, this picture is not very beautiful. I just made it this morning, but this is what dipleton is. So schematically, and now I'm completely switching gears, and I'm going to talk about completely different things. And I should say that I'm new to this field, and I'm glad some people from this field came here and will probably correct me or can ask questions. I will be very happy to interact and answer, or actually maybe not answer, but listen to them. Right. So similar to this non-perturbative configurations, let's look at another problem in statistical mechanics. By the way, my previous description works in the imaginary time, and then there is a well-known mapping between quantum mechanics and 1+1 dimensions to the two-dimensional statistical physics. So this is the so-called limit shape phenomena in statistical physics. Some of the examples of this is, for example, when you take a crystal and you cut it at some random angle. So the atoms in the crystal start to move and they try to minimize some functional, which includes the surface tension, and in the end you can have some beautiful picture like that, the upper one or slightly below. So there is a problem of random tiling where this phenomenon appears. There was a problem in high energy physics where the representations in terms of Young tableaus were also studied statistically, and there was some limiting shape of very large Young tableau. And this is a vast area, and starting from late 70s and till the recent days. So what I will take one example, and I will probably try to tell you what it is, and in the end give some our new results. So let's consider the example of domino tiling. So the statistical physics example of how essentially combinatorial problem when you take a bipartite lattice and you connect every 2 points on the lattice by dimers, or you can represent it as taking a chessboard with, again, bipartite, which has black and white squares, and trying to tile the chessboard with 1 by 2 dominoes. And you have many ways of doing this for the square board. And actually, you know how many ways you have to do that, because there is a beautiful formula. It's in terms of this double product by Castellane, which is quite beautiful in quotes, because one of interesting features is that the numbers you're multiplying are not integer, but the answer is integer, right? So there is a kind of very tricky and fine tuning here in this formula. And this number is, of course, quite big and typically grows exponentially, the exponent of the area with some number. So one way to represent this was, okay, once again, just the board became bigger and have 10 to the 197 approximately. It's one among 10 to the 197 configurations. Just to make this a little less boring, let's do probably the first thing you did when you were a child. Let's color different tiles in different colors. So colors, there are 4 different types of tiles. There is 2 vertical ones, but they're different in their kind of black and white content, right? So one has black square on top and one has black square in the bottom, yellow and blue, and 2 horizontal one when the black squares on the left or on the right. And just again, let's run a simulation, which I don't run simulations, but this is Jean-Marie Stéphane from Lyon, who does these simulations very well. And the picture looks really beautiful. So you start with a board 16 by 16, then 64, 64 to 156. You don't see really any structure here. It's a random field. It's actually a random Gaussian field. So it's a typical configuration of a random. So this is a space-time picture of Luttinger liquid for you in statistical physics. Just a random Gaussian field, one configuration of the Gaussian field. Yeah. Now, the way to, and there is a way, as I said, the number of this configuration grows as exponent times in exponent of the area of the chessboard. And it's a huge number. There's a nice mathematical constants appearing. Now let us do the following thing. Let us sort of change the board. Let's, instead of like square board, let's use so-called Aztec diamond board, which is pretty much obvious how it is constructed. You just add some vertical and horizontal rows and columns of squares. So in the end, it takes this diamond-like form. And it also supports many configuration of tiles. But there is something which you probably already noticed here, that in the end of the day, the corners of this diamond should be covered by tiles of the same color. So they are sort of you don't have very much freedom on the left and on the right, on top and on the bottom. In the middle, you do have a freedom. Now, how this develops when I take the bigger and bigger size of the system? So it develops into this sort of nice shape, which is the following. So again, as I said, the top, bottom, left and right are completely frozen in one configuration, and in the middle you have a picture similar to the one I have shown you with a square lattice.
I don't get why the corners are, you have a constraint that
yes,
colors, but the next row, why?
Right, it's true that actually with exponentially small probability you will get something different there, but number of these configurations divided by the total number of configuration goes to 0, pretty much as like 1 to the 10 to the 197 in the previous example. So it's a very extremely rare event. So a typical configuration looks like that. I mean, the circle in the middle is also has some sort of fluctuating boundaries. So that's one of the interesting questions to study, which has been studied. The whole corner, or the
yellow part, for example, the top corner, there is obviously a length scale there, right?
Oh, it's pretty much you inscribe a circle, and so that's the width. So essentially, well, I don't know, to do it 1 minus 1 minus pi over 4, something like that. But there is a fluctuating region which you, Satya, would probably know much better than me how it's, right? Okay, so and by the way, there is a kind of nice mathematical formula for number of configurations, which is again exponential in the area of my Aztec diamond, but in fact it's much less. It's just 2 and not e, but it can be computed. It's computed exactly. Right, and there is was a subject of a mathematical theorem by these 3 people who essentially said that a typical configuration for most of the configuration with some measure 1 will look like the inscribed circle, which has density. Well, I shouldn't say density, which has sort of color mixture, which is not one color. So maybe probably will be some sort of gray if you add up blue, yellow, green, and red, while there are frozen regions at the corner. And the circle is inscribed inside the square. Right. So there are other examples. Well, first of all, this picture is very universal. So there are other examples of limiting shape phenomena. It doesn't really depend on the type of the lattice. You can do the same game on the hexagonal lattice. You have like 3 types of tiles and 3 colors. What you gain though is this nice kind of 3-dimensional picture. So you have some sort of random height representation, which is quite useful for looking at the surface of a random crystal. Now, it's known that this system are equivalent to free fermions. I'm actually going to use this fact quite heavily. However, you can you can do the same time phenomena appears in interacting models like this 6 vertex models studied by one of the conference organizers back in 2004. And recently it's still a kind of active field of research. And therefore, so again, one gets sort of what is shown here is essentially the fluctuating region. The frozen region is white. And here this fluctuating frozen region is either black for total occupancy and white for empty. Are there any questions so far?
Yes, I feel that it may be important. I still don't, if you go like 3 slides backwards, first time showed this, I just missed it.
This one.
One more. Yes. For instance, on your right lower, color diagram, why is it that the 2 bricks on the second row are yellow necessarily?
I think that in this particular case, well, you have to draw this chessboard. So I know why. So I can definitely explain. So this, this is black, white, black, white, black, white, black, white. So this is green one, because it has a different content of white and blacks than this one. So this is black, white, and this must be black, right?
So there is some rule.
There's a bipartite lattice. So you have to cover a chessboard essentially. So there is some rules. Yes. Yeah. So there is the coloring is there is some but I mean, for example, here you can probably have, instead of this green and red, you can have like blue and yellow horizontally here on that side. You can swap them. It will be eligible configuration. There are many configurations in the middle, but they all have these colors on the corners. Right. So let's now assume. So as I said, I mentioned already free fermions. What I really mean by that is the following. Let's take a stack diamond. Let's attach the whole wall of red bricks on the left. Right, you can see that, and all kind of vertical wall of green bricks on the right. I mean, essentially, this is just filling the picture. Replace them by dimers of essentially the same color. So we have a picture like that. And now let us superimpose this dimer picture with a reference configuration which has only red bricks like that. Continue. So you will see that some lines will get connected, some lines are still broken, and let's draw only the connected lines. And this way you can start to see something like a particle which wanders around, and all particles start from the right and go also to the right. And when you don't have connected lines, you have nothing, and these are holes. You can draw the holes as well if you have superimposed everything with a green lattice. Now, it can be shown by using transfer matrices that mathematically the best way to enumerate all the configuration of this system is to use second quantization and free fermionic statistics. But before doing that, and I'm going to use this heavily, and this is actually a way to perform exact calculations. However, before doing that, I am not really interested in this talk in the fine details and microscopic questions. I am rather interested in the system in the kind of large scaling limit, and I would like to understand the properties of this cloud inside. Actually, it has been already understood. But I will still would like to know how to do that. So instead of using particles, I'm going to now use their densities. I will, like in Latinger liquid, and precisely this is the sort of Latinger liquid, or rather to say non-linear Latinger liquid approach, I will introduce density and velocity fields. And I will ask what is the most probable hydrodynamical configuration. I will write down a weight for these fields, for any configurations of these fields. And this is a standard hydrodynamical action. I'm not writing it down. Yes.
How do you actually construct the velocity? Velocity I can understand. What from microscopic wall lines?
Yes.
How do you construct these velocity?
Well, so the density is okay. So there are different methods. So density is like the sum of the delta function of x minus.
Yeah, I understand. Velocity, how do you g of x how do you construct?
It's related to, well, then for this I have to consider my the transfer matrix and write down some operators. I really don't remember the details, but you can do that pretty much like you do this in the path integral. So it's probably in the end it's just sum over particles vi times delta x minus xi and coarse grain it. But there is a precise procedure. Right. So, and what is, and what I require that this is kind of, now I have some kind of effective liquid which flows from the state which was empty on left and filled on the right and ends up in the same configuration. And it can do whatever it wants in the middle. Essentially, my particle can do whatever they want. The only thing they need to do is to minimize hydrodynamical action. So essentially, I'm looking for the non-trivial configuration of hydrodynamical fields. And if I find one, first of all, I know how it looks like. It looks like this Arctic circle. And I can also evaluate what is the probability of this configuration by just taking the semi-classical approximation. I'm saying that all my huge sum over all possible configurations is dominated by the one which is this Arctic circle. And that's precisely the same as what I did in the Dipleton. It's essentially semi-classical approximation. Okay. So now I was talking about statistical physics. Now I would like to do something in between. So it was a question which was asked in the integrable community. What is the probability in a ferromagnetic spin chain to have a region of finite size which has, say, all spins are up, but you want to see a line of an interval of spins down? What is the probability of such an event? So the simple question is the same question as to ask if you have some gas of fermions and you want to see a certain region or interval of certain size which has no particles at all. A similar question is asked in the distribution of eigenvalues of random matrices, and it was a very sophisticated exact calculation for spin x xz chain by Kurepin. They probably went to like 3 particles, 4 particles, 5 particles. So Sasha Abanov asked the question whether you can use this same hydrodynamic approach for a large number of particles. And the answer, again, was given by writing down the hydrodynamic action for fermions, finding a configuration which satisfies equations of motion and the boundary conditions. Well, before that, I have imposed boundary conditions on 2 time slices. Here, I impose the boundary conditions at time 0, but also actually I impose the boundary condition in infinity because I would like to make sure that my system is in the ground state. And if I do the calculations, or actually I just simply copy paste the calculations of Abanov into my slides, what you see is a quite beautiful example of the limit shape phenomena in quantum mechanics, because what you see here is imaginary imaginary time path integral, and the optimal configuration of the density looks like this nice figure here, which is described by a certain complex analytic function. And if, well, maybe you don't see very much details there, but this is a simple plot of a real part of certain complex function, a very simple one. The emptiness region, where in the space and time looks like this asteroid curve, which is given by this equation. And then one can substitute this into the action and calculate the probability of having no particles in an interval of size r in this system, and it's given by is exponentially small. It's exponential minus essentially the area of this asteroid figure in the space-time, and this NKFR is essentially the number of particles missing from that interval. But it's also interesting to see that actually in the space-time it gives rise to some interesting space-time, so two-dimensional structure, and this is full analogy with the Arctic Circle configuration. Okay, so now I'm essentially, how much time do I have? I probably was talking too much. Misha, do I have?
Misha's one.
I have plenty. Oh, yeah, okay. Right. So let's go back to particles and do some calculations on our own. So let's start. As I said, my word lines can be represented as a quantum particles, which are fermions. The lines are never intersecting, by the way. In statistical physics, this is the result of for example, in crystal, we pay too much energy for the intersections. Right, and let's start with the state below. Let's call this kind of initial state psi 0, which has zeros in the occupation number formulation, zeros on the left, ones on the right. Take the state by using the transfer matrix approach. You can essentially show that what you are after, if you want to enumerate all number of states of the system, is to take the state, apply a quantum Hamiltonian, which is a very simple one, which is a tight-binding Hamiltonian, and apply it take this quantum evolution of the imaginary time for the time 2r, and then you go back to, and they take the overlap with the same state. We can also write this as a trace of the evolution operator times the projector onto the half empty, half full line. So this and this way you can actually do the calculation. I will show how to do that. You get the answer for this particular type of the lattice, which is again exponential to the area of the Arctic Circle divided by 2. Now, in quantum mechanics, if I take my time to be real and not imaginary, I simply have to change the sign in the exponent, and it's known as a Loschmidt echo.
This result of this e to the power minus r square over 2, this is also the same as in GUE. And the reason is obvious because the ground state of these non-interacting fermions.
Yes.
This is exactly
yes.
Exactly same in terms of GUE matrix. And there it's a well-known result that if you have a gap probability.
This is not a new result, by the way. Yeah, sure, absolutely. I will come to random. I will come to random matrix. Yeah, of course. All the semiclassics in all my talk is there is a large parameter. Here it's a large R. In my kind of short introduction, you also should suppose that the action of a dipleton is large, and and actually it's an interesting story on its own. It's essentially this logarithmic divergence in the action which controls the precision of the dipleton model, right? Okay.
Yeah, so your time, as far as I understand, or imaginary time, evolves from the left to the right. Is that it? So
No, it evolves from bottom to top.
Bottom to top. So you impose the minimal boundary condition at the bottom.
Yes.
Rather than enforcing it on the side of your dimensional plane.
No, yeah. So well, probably quantum mechanical picture is is better. Your initial state psi
Yes.
is the domain wall psi. It's a kind of infinite Fermi surface in real space. You put particles only on the positive semi-axis,
Yeah.
and no particles on. And then you start with the state.
But that's the initial boundary.
Yes.
And yeah, probably that is because I didn't quite get what the statement of the problem was, because it seems to me probably that wanted to put the boundary conditions on the sides.
No.
Sure. Okay.
No, there are no boundary conditions on the sides imposed. So the particles can do what they want.
Okay.
And the larger R is, the farther away they go.
Sure.
And yeah. Right. So let's entertain ourselves with exact fermionic calculation of Arctic circle. So let's take these two states. But now the problem, I was kind of lazy, and I decided that I don't want to consider infinite number of particles, which was in the previous example. So now we'll take a finite number of particles and see what does it leads to. So but anyway, we believe that everything can be recovered in a certain limit. So let's take the initial state, which has n particles present, all the rest of the lattice sides absent, and the same state will be in the future after time 2r. Of course, n and r are large number, and let's keep their ratio n divided by r fixed and call it lambda. And let's calculate precisely this number of all possible configurations, or if you want, this kind of restricted partition function, which is given by this formula here. And I attached the symbol n because I'm, as I said, work with finite number of particles. Hamiltonian is reformulated in the K space. The dispersion for the type by the model is cosine K. Okay, some heavy machinery, but pretty much straightforward one. Everything, initial state can be created by creation operators at time minus r, which create particles from 1 to n on the sides from n to n. Then you propagate and you destroy them with annihilation operators at time plus r on the same sides. That's all. And these operators act on a completely vacuum empty space. Now, this calculation is pretty much standard. It's given by determinant. Determinant can be collected into if you take this green function cy cx different times and write it in the K space Fourier transform, and in the end of the day, you end up with some interesting integral over n momenta of the particles, which has a familiar structure for people from random matrices, because it contains the so-called van der Monde determinant. That's essentially the sort of ground state. It would be the ground state of particles if I put r equals to. Okay, so I don't want to say something. I mean, it's essentially a Slater determinant of fermions, but not in a problem which is probably related. Anyway, mathematically, this is the one.
Your first equation is Zn is the expectation value of power minus 2rh.
Yes.
Which is fine. And the second equation is power minus 2rh has completely disappeared. And what is it?
It's hidden in the time labels of my operators. It's minus r and r, so I just take the Heisenberg evolution. Sorry about that. So I said that boundary time slices. I try to make sure that.
So H acted on psi,
yeah,
and sliced with psi.
Yeah, but psi itself is the result of applying this string of fermionic creation operators.
So in a way, this factorization has happened, that you have, instead of this psi and h blah blah blah, you have a product of individual evolutions of whatever from C1 to Cn twice. I mean, the evolution, this exponent for each C, the part of this exponent hopped into the C1 of minus n, Cn of minus n. So it's all Hamiltonian is acting in a way on each seat.
But that.
Yeah, but it's a standard time Heisenberg time evolution of operators. Yeah, that's the definition. I think.
So this is.
In the end of the day, you get this interesting.
Can I also comment on this type of integral? So basically, if you compute this integral with epsilon being cosine, you'll get just Bessel function. And this integral is actually will be some type of, let's say, a Toeplitz function with this Bessels. And in fact, it's known that Zn is exactly e to the minus r square, not just asymptotically, but exactly. So this is very nice.
Sorry, the last sentence, please.
So your result that z is e to the minus r square, something, right?
Yes.
It's not asymptotic, it's exact.
Okay, wait. Yeah. Okay, so you're saying that this is an exact.
Yes. So.
Okay.
So.
No.
So
I mean, asymptotic in terms of a large R, of course.
Yeah. The easiest way to see it is okay. Asymptotically, you okay. Since this is Toeplitz, you can start apply this Siegel theorem. Yeah, and yeah.
Okay. Yes. So by the way, yeah. So I didn't mention this connection to Toeplitz determinants, of course, but this configuration, this n-dimensional integral, is actually a very well-known thing for epsilon equal to cosine. And I would like to represent this under this name.
Yes, we hear you, Greg. Go.
Well, actually, in 1970, high energy people, quite known one, were writing down a theory for lattice QCD for particles with many color flavors, describing them with large unitary matrices, and we were able to write it down as one single integral on one. It wasn't a big lattice, but in the end, everything is essentially boils down to one integral, which is precisely the integral I have obtained on the previous page. Precisely the same. Right now, the parameters I have chosen, I even chosen to call this the same name. The time R is n divided by lambda, and this is how it appeared in the Gross-Witten-Wadia model. So we end up with Gross-Witten-Wadia model. And Gross-Witten-Wadia model, now let's, what is the main beauty about it is the following. Now let us ask now, what is the dominant configuration of those momenta here? Essentially, we are asking the question, what is the dominant configuration of our fermions? What are their momenta? What are the typical momenta we will see if you measure them? And the answer is the following. So, okay, so in terms of the exponential of ik, you are in the complex plane, and my numbers sit on the unit circle. For when the cosine term in the exponent is always forget is small, they prefer to fill the unit circle almost uniformly. But when the weak coupling is the coupling is sort of strong, but 1 over lambda is smaller than 2, there is a gap which appears in their distribution. And actually this can be understood, and as usually it's understood in the random matrices. You essentially have a sum of all configurations of charges sitting on the unit circle, which repel each other logarithmically, and that's the van der Monde determinant, and subject to external electric field. And this electric field tries to polarize this distribution of charges. If it's weak, the charges don't care, and by symmetry just sit all around the circle. But if the electric field is strong, the charges start to pile up into front and leave some gap on the left of the circle. Right. Good. And you can solve this problem exactly. You can essentially borrow the solution from the paper of Gross and Witten and Vadia and calculate the free energy. As I said, well, there is actually two regimes for lambda greater than 2. So when charges fill the circle, as I said, and as Mr. Gamayun noticed, that the answer is given by minus r squared, while for smaller lambda, and then it just doesn't depend on lambda anymore. But for small lambda, you have some non-trivial dependence, and there is a discontinuity in the third derivative of the free energy exactly at lambda equals to 2, and this is the third order phase transition. And our question is very simple: to what this transition corresponds in our space resolved picture of Arctic Circle? You can guess this almost immediately, and the answer is beautiful. Look what lambda is. Lambda is the distance between the circles divided by their radius. If lambda is large, two circles are very far from each other, so their contribution into free energy is simply additive, and you get the result twice e to the twice r squared divided by 2. When lambda equals to 2, the circles touch each other. Nothing changes until then. And non-trivial things start to happen when lambda is smaller than 2. So, well, what, like in this kind of stupid demonstration how teacher should behave, I should now have all this and say, well, what do you think? Let's vote and so on. Okay, I will show what's happening. But to do that, I want to essentially try to obtain the real space picture, real space and time picture from my Coulomb gas picture, from my Coulomb gas solution. Okay, so first of all, the density of charges, which I have calculated or essentially borrowed from Gross and Witten, can be written down as an implicit way as some function f of sigma and k equals to 0, and f of given by this kind of polynomial in x and polynomial in cosine k function. And here m is the sort of order parameter. It's 0 in the separated phase and and non-zero positive for lambda smaller than 2. And this is the plot of my sigma of k for different values of lambda. Right. So this is just a graphical representation of the result. But what I can say, essentially, my claim is, if I are talking about three fermions, the fermions occupy uniformly some portion of the phase space. So essentially, my implicit condition on between, essentially what I want to say, okay, this function for density of charges, which is some sort of momentum distribution, is nothing, is the position of my fermions, average position, of course. So essentially, I'm saying the following thing. Suppose I have x and k phase space, and I draw some domain in the phase space. The density of particles in the real space will be given just by the area of this blob. And as a function, sorry, for every x, it's just the height of this between these two lines. So my sort of Fermi momenta, which is essentially the density as a function of x, local Fermi momenta, are encoded if I solve this equation for k as a function of x. But now I can do precisely the same thing, but for x as a function of k. Essentially, this picture is for x as a function of k. So for x as a function of k, I can define some kind of Fermi coordinates, and that will be the x as a function of k. And I can turn my picture around and calculate the density as the difference between my momenta. So taking the
Why do they have many pointers? It's a bit confusing.
okay, sorry, thank you for this question. What is shown here is the function sigma of k for different values of lambda. Okay, sorry. I will show you much better pictures. Yeah. So this is essentially sigma as a function of k. So you can see, by the way, there's some sort of topological transition here, which I'm not to talk very much, but actually I can something to say about it. For the upper kind of outer curves are situation when curves when the circles are separated, and you can see this here when I plot just the mean density of my particle. So it's essentially is non-trivial and has value between 0 and 1 in these two separated intervals. In between, it's a frozen region. Density equals to 1 exactly, right? But then when lambda equals smaller than 2, when they're sort of supposed to overlap, the density is not frozen all the way around. So now actually even more than that, as I try to convince you that this function can be extended to different times as well, and I can have the full space-time profile by simply ballistically evolving my fermions. I can add to x time times the velocity of the particles, solve the equations at any time t, solve this equation for k as a function of x, find the density, and plot this beautiful picture. So what you see here, for lambda greater than 2, you have two identical Arctic circles, which are mirror image of each other. And this is the density profile for any time t. So t is in that direction and x is horizontal direction. For lambda less than 2, these two circles merge into this nice picture. And this is the shape of the optimal configuration. Right. Now, moreover, in fact, there's many mathematical tricks you can play. So for example, if I want to know just the boundary of my Arctic circle, what I can do, I can take my momentum k to be, by the way, to do this picture, what you have to do is have to extend this kind of Wigner function or my conditioned function f0 to complex values of x and k. Well, quite naturally, because what you add is evolution in the imaginary time, so I have to add some imaginary part to my x. But if you can solve this equation, and this is for this case, it's a simple quadratic equation. For this case, it's more complicated, but it's essentially equation of some polynomial of x and k equals to 0. So, but if you're not interested in information about the fluctuating region, you can calculate simply the shape of the boundary by saying that on the non-occupied, on the empty side k, there is no density, just velocity, which is it's purely imaginary. Inside, in the frozen occupied state, k is pi plus a velocity, and then you can solve two equations. One is the ballistic evolution, the second one, and then you can draw these lines which are given by this third line here. And the envelope of these lines, all these lines are tangential to the boundary. So you can resolve this tangential condition and describe the shape of the frozen boundary above the transition and below the transition. And finally, I'd like to look in more details at the transition itself. So let's take lambda, let's tune lambda to 2 by very amount which scales with R. So I have to take this particular value of R, and sorry, this is 2/3, it should read 2/3. In this case, you can see the just schematically, well, this is the plot of the central region when the circles touch as a just build when the two circles have sort of merged and when they have separated, and one can study the fluctuations in this area. And what we want to study is what is the probability that before the circles touch, you still can have a frozen region. It is a rare event below the transition, because normally you would rather have some non-frozen density, but spontaneously such regions can appear. And we are asking a question which is very similar to asking the questions, what is the probability to have a full or kind of fullness or iceberg formation probability? If you think about this as like two seas and icebergs and frozen icebergs inside, what is the probability to have an iceberg in between at t equals 0, so just in the middle of this picture? And to do that, all we need to do is to solve a more complicated problem, but which can be done using pretty much the same mathematical methods, to imposing another boundary condition at t equals 0 of particles, not allowing them to go into this region of certain size. And we get answers which are pretty much expected, but still beautiful. So one has, this is the typical configuration of the boundaries. Plotting the three-dimensional picture becomes quite a challenge. If I take the size of this fullness to be delta, lambda is my parameter, and in the certain rescaled version of these variables, I get as again, my probability to be exponential of the action of this optimal configuration, and this action can be calculated. And what you have a transition from x square, which is the result for simply putting from the result of Abanov, which is the size, which is the area of my asteroid region in the middle of melted, sort of fluctuating density with the local value of the density, and cubic behavior above certain value of x, which is the known asymptotic of the Tracy-Widom distribution. In the second case, the typical configurations to get this x3 cubic behavior is like that. So essentially, this is the typical configuration. Well-separated circles with some region here sort of pushed inside because of the extreme boundary conditions. Right, so I would probably go to conclude. It has a lot of more details, but I was kind of limited mostly my preparation to this stuff. So as I said, we were studying impurities as non-perturbative ray configurations of nonlinear liquid. Nonlinear Latin liquid is usually developed about some background. There is reports about density. You have to subtract the mean density. Mean density is uniform, not anything important. I try to change this talk. I essentially try to change this data. It can be quite interesting if you impose interesting boundary conditions. Impurity is one of them, right? So, okay, so we wanted to solve this question in a completely different setup, which is the Arctic Circle phenomenon, limit shape. We were able to, well, it was quite easy, but the two Arctic Circle phenomenon is essentially nothing but a gross medium model. We have a space-time resolved picture of this model, and we can space-time a picture of the third order phase transition as a merging or melting of two Arctic circles, we found the crossover between Gaussian and Drake-median behavior for the probability of full region in between frozen size of the frozen region. Well, it looks like these results can be universal, and you can apply them to the similar phenomenon in interacting models. Now, from the perspective of this work for the experimentalists, apart from the experimentalists in the statistical physics, like crystal growth and the polymers, and which is again the last area I would just want to comment that quantum mechanics is recovered and quantum dynamics recovered imaginary, and our approach is well suited because in the end, as I said, you write down this for free fermions, of course. You write down a evolution, and if you take T to IT, it's essentially changing the coefficients of these polynomials by doing that by. Sorry, so I was saying that quantum dynamics can be studied by changing, by making weak rotation, and probably a lot of phenomena can be seen on the same footing. So like quantum quench is a standard example, quantum information as quantum evolution, essentially, Flaquet evolution, time crystals, and you name it. So I finished. Any questions?
Yeah, may I ask a question or comment?
Yes. Yeah.
Do you hear me?
Yeah, I can hear you.
Okay. Yeah, thank you for this very nice talk. Actually, I was wondering, so, I mean, people have studied the collision of two Arctic circles. But of course, I mean, in your case, this is a bit different because they are related to each other. I didn't get really the why they are symmetric from one another.
Well, yes, people. So can you repeat? There is no symmetry. Can you refer to some particular slide?
Yes. So when you discuss, yeah, typically when you so the two Arctic circles that you have.
Yes.
So they are not independent, right? I mean, from one another. That's my question. I mean, or are they? Because if they are, I mean, people have studied this, and it's known that it leads to this stack node process. I mean, this has been studied.
No, that's. Thank you for this comment, and I'm sorry I didn't mention. There were already. It was noticed that I mean this problem was studied. Yes, it's related to stack node process. Our methods are somewhat different, and the questions we ask are somewhat different, and we are interested in the kind of hydrodynamical description of this stack node process. There are papers by Coloma, by Morbeke, and there are some authors which we consider, and I
Yes.
didn't mention this. I mean, I mentioned this as on the first slide.
Okay. But yeah, I mean, I was a bit surprised because there, I mean, we know that it's not exactly like tracy rhythm. I mean, it's a bit different. I mean, the stack node process is not like the Airy process, and you seem to obtain things which are more similar to Airy. I mean, because Gross-Witten Wadia is basically tracy rhythm. I mean, in the scaling limit. So I was just wondering about that.
I mean, probably we are taking, well, that's something to see. We have this, we don't really look at the Airy process itself. We look at the asymptotics, and probably it's a different scaling limit. Yeah, it's a kind of work in progress.
Okay, thank you.
So I missed the connection with observables. So you are computing this matrix element of the imaginary time evolution operator between the two simple identical states upfield the system.
Yes.
Sides, but and then you get these shapes as a function of imaginary time. But Is there some physical observable related to that?
No, this is like calculating the partition function, but this kind of observable we are trying to calculate here, you essentially insert an operator, which is the projection onto the frozen region in the middle. It's equal 0.
Okay, so in that case, it's the vacuum formation probability.
Yeah, it is. I mean, vacuum in the sense of fullness, full occupancy. It's also vacuum. That's like two extreme values of your occupation on the last slide.
And starting from which initial state?
We start with well, okay, so starting from this state, so n particles, so there are this interval is full, then interval of different sizes must be full here, and then you should go back to the original initial state.
Okay, and what happens outside of this initial region, you don't care.
Yeah, and I don't care about anything else. So particles are free. So typical configuration, I mean, once again, everything is dominated by one single configuration, which looks, well, depending on the regime, it can look like that, for example. So particles have to avoid this region. Otherwise, they do what they want, and that results in some complicated expression for their density.
I just wonder, maybe it's not really related, but I wonder about this hydrodynamic action method, whether you can apply it for the just emptiness formation probability on the real line, where you have just sine kernel. Because there asymptotics, it's not just e to the minus x square, but also it's corrected by some power, like 1 of x to 1/4 or something. So I wonder if you can just get it from hydrodynamics, or it's like.
So that's about calculating the fluctuation determinant, and it's essentially beyond. We are really mean field. We just look at the optimal solution at the moment.
Mm-hmm.
The study of fluctuations is in the pipeline. Any other questions? You can thank the speaker again.
I stopped recording.